Okay, hello. So we're here to do chapter 4 of Cisco 3, and so it's about Ether Channel and HSRP, or Hot Standby Routing Protocol. So, of course, Ether Channel is a link aggregation protocol, which basically means you can join more than one link together and both up the bandwidth and also link utilization as well as reliability as well. So, and then we'll look at how we configure that, and then we'll also look at first HSRP, which is a first hop redundancy protocol. And so hot standby routing protocol is a Cisco proprietary version of the first hop redundancy protocol. So link aggregation. So basically we've already done spanning tree, and so with spanning tree, if you have more than one link to the same area, you will have a loop, and so it will actually block that link, one of those links at least, so that it will stop a switching loop, and of course stop broadcast storms and the like. That's good. You have redundancy. If the main link fails, that blocked link will become unblocked, and you will have traffic going through, and that's very nice. But I'm going to say 99.999% of the time, that primary link will be good, and so you've got that link sitting there and not getting you any benefit really, other than a bit of peace of mind. And so by using Ether Channel or another link aggregation protocol, you can combine those two physical links into one logical link. And so basically you can actually configure that logical link as if it were a physical port. You can change its settings and the like, and they behave as one. Also, spanning tree treats it as one link, and so both cables will be available for use, and so you can double your bandwidth. And also, if one of the links does fail, it will not break it, it will just go back to a single link, and so you haven't lost any reliability or redundancy, but you've got the advantage of being able to use the bandwidth of those links 24/7. And so basically the traffic is load balanced across the two physical cables, and so it doubles your bandwidth basically. And so what implementation restrictions do we have? So of course you group multiple physical ports into one logical Ether channel link, and so the interface types cannot be mixed, and so you can have some fast and some slow. They need to be all the same speeds. They all need to be fast Ethernet, or they all need to be gigabit Ethernet, or whatever it might be. And so that's one restriction. So it gives you full duplex bandwidth of up to 800 megabits per second. So you can combine 8 physical ports together to make that faster one. If you need more than that, that's probably when you're using a lot of ports on your switch, and you might as well just buy a switch with a faster port, so get a 10 gig Ethernet link. And so most iOS switches will support 6 Ether channels. You've got to have a lot of ports to be able to do 6 channels of 8, but so created between 2 switches or a server and a switch basically. So if one side is configured as a trunk, the other side must be a trunk to stay with the same native VLAN. Each Ether channel has a logical port channel interface, and changes to the channel affects its physical interfaces. And so once you've combined multiple physical channels into this Ether channel, you need to then do all your configuration changes to that logical port channel interface, not the individual interfaces. Now, basically, there's actually 2 possible protocols you can use. With PAGP, which is Cisco proprietary, or LACP, which is a standards-based one. Now, there are different mode commands. They behave in very similar manners, but they just, by using different commands, it specifies which version of Ether channel you're going to use. And so with PAGP, you've got the option of on, desirable, or auto. Now basically what that does is on makes it a channel member all the time. There's no negotiation involved. Then there's desirable or auto. Basically, with desirable, it wants that to be an ether channel, while with auto, if the other end wants it to be, I'll be good with it, but otherwise I don't particularly want it. And so, as you can see, there's a table down below. Basically, if you have on, it will on switch 1 and on switch 2, it will be an ether channel. Cool. If you have auto or desirable at one end and desirable at the other end, it will not. It will work. I mean, if you have on auto desirable and not configured at the other end, you won't get it. If you have on and desirable, because on doesn't negotiate, it won't work. If you have auto at either end, both ends, it will not. So you need desirable at least one end for the negotiation to work. Or of course you can just set both ends to on, basically. Now the default setting is actually auto, and so basically with LACP, it's on, active, or passive. So on is, again, no negotiation, so you don't need a protocol. Active is the equivalent of desirable, and passive is the equivalent of auto. So they behave in basically the same ways, but they're the different protocols, basically. And so, yeah, as I said, LACP is a standards-based version of it. So how do we configure it? So basically, configuration settings must match on both switches. They must have the same speed and duplex mode. All interfaces in a bundle must be assigned to the same VLAN or configured as a trunk. The trunks must support the same range of VLANs. So there's a whole pile of things you need to sort of I's to dot and T's to cross before it will work. And so basically, as you can see from the diagram, the speeds are the same, the duplexes are the same, and the VLAN is the same. If any of those are different, so here the only difference is one end is half duplex, the other end is full duplex, it will not happen. And so yes, you need to make sure that works. Now, how do we configure it? So of course, using the interface range command will speed the process up, and of course it will ensure a bit of consistency within the switch. And so so you need to specify the interfaces that compose the ether channel group, and then you type in the channel group, give it a number. And so of course, channel group 1 will be those interfaces will be in channel group 1. If you need to put another ether channel, then you need to use ether channel group 2 or some number other than 1. And so then of course you do mode, and then it's either going to be active or passive or on or desirable or auto. Basically that's what you will do. But of course we're talking about LACP here, so it's either active or passive. And so from there you've done that, and so then because you've done that channel group command, there is now that new logical interface called the interface port channel 1. And so then you can do switch port mode trunk, and then switch port trunk allowed VLANs or whatever. Of course, if you don't do the allowed VLANs, it will allow all VLANs. But of course, you've got to remember that you've got to make that the same on the other end as well. And so once you've got it all configured, you can actually do show interfaces port channel 1, and it will show you information about it. Or you can do show ether channel summary, and it will tell you about what ports are in it. As you can see, there's port channel 1, and there's fast Ethernet 01 and 02 in there. And it tells you that LACP is the protocol. And then S and U, of course, you have to look up here to see what that is. So S means it's layer 2, and U is in use. So it's a capital U. Okay, so show ether channel port channel, and we'll give you more specific information about the channel groups. And there's also show interfaces fast Ethernet 0/1 ether channel, and it will tell you about what channels that particular physical one is in. And so how do we troubleshoot it? Well, basically, it's going back to what was said in the slides before. So you have to have compatible speed, duplex, native and allowed VLANs, and of course they need to be members of the same VLANs. And so you've got to make sure that you have matching settings. And so you'd probably do a show run and compare what settings you've got. Okay. And so here we've got a port channel and its status is SD. So S means it's layer 2, D means it's down. So we've got a problem. And so from here, on switch 1, we've got mode on. We've got mode on both of the physical interfaces, and we've got the port channel, which is switch port mode trunk. We've got switch port mode trunk on switch 2, but we've got desirable. And so this is wanting to negotiate. This is a no negotiate. So we've basically broken a rule there. And so you would either need to put these to be on or these to be auto, basically, to fix it. And so here, we've now got it to be running, and so we've got S and U, which of course is layer 2 switching, and U is in use, or up, I suppose it could be as well. Okay, so first hop redundancy protocols. And so, of course, having redundancy on your first hop routing routers is not easy because basically most hosts, you can only ever put one gateway in as a configuration information. And so a mechanism is needed to provide alternate default gateways in switch networks where 2 or more routers are connected to the same VLAN. Note in the graphic, a multi-layer switch is acting as a default gateway and used for routing. In a switched network, each client receives only one default gateway. There is no way to use a secondary gateway, even if a second one does exist, to carry packets off the local segment. In the figure, router 1 is responsible for routing packets for PC1. If R1 becomes unavailable, R2 can route packets that would have gone to R1, but of course, telling your end device how to get that done is the tough bit. And so end devices are typically configured with a single IP address for a default gateway. If that default gateway IP address cannot be reached, the local device is unable to send packets off the local network. So, problem, redundancy is a bit tougher. So, how do we get some redundancy built in? And so, basically, we have, in this case, there are 2 physical routers, and so there's the forwarding router and the standby router, and together, through configuration, they create this virtual router with the same, which they share the IP address and MAC address for. And so basically this forwarding router is the one that is actively doing it at the moment. If it were to fail, the standby router would, after at least a period of time, figure out that, oh, it's down, and so it would take over that virtual router, and so the packets would actually go out the alternate route. So to prevent a single point of failure, the default gateway, implement a virtual router. So you present the illusion of a single router to the host on the LAN. By sharing IP address and MAC address, 2 or more routers can act as a single virtual router. IPv4 address of the virtual router is configured as the default gateway for the workstations on that segment, and so that all have 192.0.2.100. The IPv4 address of the router is configured as a default gateway. ARP resolution returns the MAC address of the virtual router as well. Physical router that forwards the traffic is transparent to the host devices, and so they don't need to know. A redundancy protocol provides the mechanism for determining which router should take the active role in forwarding, and the ability of a network to dynamically recover from the failure of a device that is acting as the default gateway is known as a first hop redundancy protocol. So, what steps for router failover? So when the active router fails, the redundancy protocol transitions a standby router to become the new active router. So these are the steps that take place when an active router fails. The standby router stops seeing hello messages from the forwarding router. The standby router assumes the role of the forwarding router, and because of the new forwarding, the router assumes both IPv4 and MAC addresses of the virtual router, and the host devices see no disruption in service. Well, there might be a momentary disruption, but it won't last very long. So we're talking about HSRP, or Hot Standby Routing Protocol, in this chapter, and so it's a Cisco proprietary first hop redundancy protocol designed to allow for transparent failover of a first hop IPv4 device. Active device is the device that is used for routing packets. The standby device is the device that takes over when the active device fails. Function of HSRP standby routing is to monitor the operational status of the HSRP group and to quickly assume packet forwarding responsibility if the active router fails. There is also HSRP for IPv6, which is basically the same, but of course redesigned for IPv6. And so HSRP defines a group of routers, one active and one standby. You have a virtual IP and MAC address that are shared between the two routers. To verify the HSRP state, use show standby command. It is Cisco proprietary. There is VRRP, which is a standardized protocol, but we're not talking about it today. Okay, now there is VRRP version 2. Virtual Router Redundancy Protocol is a non-proprietary protocol that dynamically assigns responsibility for one or more virtual routers to the VRRP routers on IPv4 LAN. One router is elected as a virtual router master, with the other routers acting as backups in the case of the virtual router master fails. There is a version 3 which is compatible to IPv4 and v6. There are other protocols as well. So there is Gateway Load Balancing Protocol. So it does the redundancy, but it also does load balancing. And so that's pretty cool. And of course, there's GLBP for IPv6 as well. But of course, GLBP is Cisco proprietary again. So, So an overview of HSRP is one of the routers is selected by HSRP to be the active router and default gateway. The other router will become the standby router. If active router fails, the standby assumes the role of the active router and default gateway. Hosts are configured with a single default gateway virtual address that is recognizable by both the active and standby routers. And so basically, HSRP version 1 compared to version 2. There's a lot more options for group numbers with version 2. Uses a different multicast address. And of course, it also supports IPv6. The virtual MAC address is pretty much the same for all of them. Just the last 2 digits will change with the group number. And so with the IPv4, again, yeah, it's got a range. And so they've also added authentication to our HSRP version 4. But and we're always going to use group 1 in our labs. So basically that's all very wonderful, but we can manipulate the way it behaves by actually changing some settings. And so we can actually change the priority of routers, and so we can manipulate which router will normally be the default router. And basically, so the role of active and standby routers is determined by the election process. By default, the router with a numerically higher IPv4 address will be the active router. That's I'm going to say you need a tiebreaker by all means. You can control the election with a priority and not use the highest address. And so basically, priority is used to determine the active router. Default priority is 100. And so the range is 0 to 255, with the higher number being the higher priority. And so you can use the standby priority interface command. So standby priority, and I think you need to supply the group number and then the priority. So that's wonderful. Now, with preemption, basically, if the primary router fails and of course the standby takes over, when the primary comes back again, by default it will stay the standby router because there's been no failure. The what was originally the primary router will then be the standby, because, well, the other one's doing the job, it's working, so why change it? Well, you might have reasons to change it, and so you can actually use the standby preempt command, where when the primary router comes back again, it will take over being the active router again. Now, the reason you might do that is you might actually have optimize the traffic that you send through the router for different subnets to use a particular router, and so so you might, of course, want it to come to be useful once it's used as soon as it's up again. Okay. Now, what states do we go through? So it's initial. This state is entered through a configuration changer when the interface first becomes available. And then you go into learning. So the router has not determined the virtual IP address and has not yet seen a hello message from the active router. In this state, the router waits to hear from the active router. In listen mode, the router knows the virtual IP address, but the router is neither active nor standby. It listens for hello packets from those routers. In speak mode, the router sends periodic hello packets and actively participates in the election of active and or standby routers. In standby mode, of course, the router is a candidate to become the next active router and sends periodic hello messages. Of course, active means that that is the router that's forwarding packets, and it is using the virtual MAC and IP addresses, and it sends out periodic hello packets. So the active and standby HSRP routers send hello packets to the HSRP group multicast address every 3 seconds by default. Standby router will become active if it does not receive a hello message from the router after 10 seconds. And so there will be a pause in failover. You can lower these timings by to avoid increased CPU usage and unnecessary standby state changes. Do not set hello timer below 1 second or the hold timer below 4 seconds. Okay, so how do we configure it? So you can do standby version 2 if you wish to change the version 2. 1 is the default. And then you do standby, group number, and then the virtual IP address. And so and then you can do standby, again the group number, priority, and then give it a number. And then you can also do standby, group number, preempt, and that will basically do your settings. And so if you wish to change priority, if you want to set a router to be the active router by default, you would set it to a number greater than 100. And of course, if you want it to always be active whenever it's up, you would do the preempt command. And so here's some examples on routers 1 and 2. And so you've got IP address of 10.2 and you've got 10.3 on R2. You've got standby version 2 put in there, and you can see that the virtual IP address is 10.1 and it's been set the same on both. But on router 1, it's got the priority 150, so that will become the active router, and of course preempt, saying, hey, I'll take over. And then once you do that, you do no shutdown, and away you roll. So there were only 2 commands required on router 2, but there were 1, 2, 3, 4 commands required on router 1 to get it the way they wanted. Okay, so how do you verify it? As this earlier slide said, show standby. And so it tells you the state is active for router 1 and state is standby for router 2. And so it tells you how many state changes there's been, what the virtual IP address and preemption and so on. And it knows who the standby router is. And of course, the standby router here is local. And so you can also do show standby brief. So it gives it all to you in one line per standby group. So of course, if you've got inter VLAN routing, you would probably do this on more than one, on all the interfaces, the sub interfaces, and so you may well have more than one standby group, basically. So how can it fail? Most issues will arise during one of the following functions: failing to successfully elect the active router that controls the virtual IP for the group. You can have failure for the standby router to successfully keep track of the active router. You can have a failure to determine when control of virtual IP address for the group should be handed over to another router. You can have failure in devices to successfully configure the virtual IP address as their default gateway. So the kinds of problems you can have. You can actually debug standby, errors, events, packets, and so that will, they are the options available. And so it'll, of course, put an output to the console every time something happens with HSRP. Okay, and so they've done debug standby packets, and so every time you see a packet going to and from the router for that, you'll, as I said, get a line. Okay, and so basically from there, they turn off router 1, and you can actually see what packets happen, and of course the end result is that the router 2 will now move from standby to active mode. And when R1 comes back again and it's got preempt, it will actually basically take over the standby route, and so the end result is R2 will now be R1 standby router is 1, and then speak to standby. Now, if a router fails ungraciously, you've got that timeout that happens. If you actually do a shutdown command on an interface that is the active one, it will actually send a resign message. So at least it will go and say, hey, you got to take over, I'm shutting down, before it actually does that. And so that's at least a nice graceful system, so that the standby router can take over straight away, doesn't have to wait for the timeout, basically. So that's certainly a good system. So configuration issues. So HSRP routers are not connected to the same network segment. That's bad, although this could be a physical layer issue. It could also be the VLAN subnet sub-interface configuration. So that's one problem. HSRPs are not configured with IPv4 addresses from the same subnet. That's bad. If they're on the same physical address, physical network, they need to have the same network address. HSRPs are not configured with the same virtual IPv4 address. That is a problem. HSRP routers are not configured with the same HSRP group number. They won't keep track of one another then. End devices are not configured with the correct default gateway address, which of course should be the virtual IP address. And so, although not directly related to HSRP, you don't get the benefits of HSRP. So, that's the end of the chapter, and so we've looked at link aggregation using LACP or PAGP, and we've looked at how it works and how to implement it, and we've also looked at HSRP and how to implement that. There's the logo. So that is chapter 4 done, and yeah, we'll catch up with chapter 5 later. See ya.